Hey guys, just wanted to give you a few hints on practice problem 5.1.1. So here we go. We've got this blue frame, this blue rectangular frame, and we've got some different forces acting on it. And so it wants the force resultant and the angle that goes along with that. So that angle that they're talking about is going to be the angle between the x-axis, which is horizontal, kind of like this BC line here. So they want the angle between that and whatever the resultant force is. And the resultant force is just going to be the equivalent force, the single equivalent force that would match if we combined FA, FD, FC, and FB all into one force. And the way we can do that is kind of similar to what you've been doing through a lot of the semester, and that's take all of the x components, or all of the forces in the x direction, so all of FA, all of the x component of FD, so that would be something like cosine times theta times FD, plus x over h of FB, and then obviously there's none of FC that is in the x direction, so you'd add up those three, the x components, and that would be the sum of the forces in the x. And then you'd sum all the forces in the y, so there are no forces in the y from FA, all of FC is in the y, it's negative, and then to get the force in the y direction from FD, you just take the sine of theta times FD, and from force B, you'd take y over h times FB, and that would be negative as well, right, because it's pointing down. So then you'd add up all the forces in the y, you'd add up all the forces in the x, you'd take the square root of the sum of the squares, so you'd take the square root of the sum of the forces in the x squared plus the sum of the forces in the y squared, and that would give you the magnitude of the force resultant. And that's what they're looking for. And I'll post this Mathematica notebook so you guys can kind of follow along through that if you want. So we sum all the forces in the x. One thing to watch for here is that you've got to put in this degree word, and it has to be capitalized to get Mathematica to give you degrees instead of radians. And also I like to put in / capital N at the end of my stuff so that I can get decimals out instead of funky combinations of square roots and fractions and stuff. I can read it more easily, I think. Same thing in the y direction. And then to get so I put it in vector form because I wanted to see it that way. We don't actually use that. But then to the square root, you just put in control 6, and then whatever you called your sum of the forces in the y and your sum of the forces in the x. And we get that value. Now they want the angle between, excuse me, the x-axis, which is in the BC direction, and that resultant force. So what's that going to be? Well, let's imagine the resultant force kind of the same way we did with like FD or FB. Let's look at FD actually. For this, to find the forces in the x and the y direction, we took the sine of theta and multiplied it by FD, for example, to get the y direction. Well, we're kind of working backwards from that now because we want the angle, and we have the x direction, and we have the y direction for the force resultant. So we want to find something that, given x and y, will give us the hypotenuse. And the way we can do that is with something like an arctangent. Tangent is opposite over adjacent. So if we use opposite from the angle being the sum of the forces in the y direction, and the adjacent being the sum of the forces in the x direction, then we can take arctangent, and that will give us the angle. But since Mathematica likes to give angles out from that kind of a function in radians, we have to add this funky business, this n square bracket, and this slash degree, and then close off with another square bracket to get it to give it to us in degrees instead. So we get a negative degree angle. And what does the negative mean? That just means that it's going down from the x-axis instead of up, which you can imagine makes sense. All right, so let's now look at the part where it asks for the moments about different points. And I'll just show you one, and then I think you'll see the pattern and you can kind of go from there. So about point A, what moments are caused about point A by these different forces, FA, FD, FC, and FB? Well, if we imagine holding on to this frame, this blue frame, this blue rectangle at point A, and trying to resist these forces, what would it be like? Well, as far as twisting goes, all I care about here, I'm going to have a little bit of a paradigm shift. I don't care about forces pushing or pulling straight in line with the point that I'm looking at. All I care about is, does it try to make the frame turn? So at point A, if I'm holding on to that, FA doesn't do anything as far as turning or twisting the frame goes about point A, because it's in line with point A, if that makes sense. If you can imagine, if there's someone pushing straight in the positive X direction on point A and I'm holding on to it at point A, it's not going to cause any sort of twisting or turning motion about that point. And same thing with the X component of FD. Because it's going in the same direction, it's just pulling this way, it's not going to cause any twisting or turning about point A. What is going to cause some twisting and turning about point A, though, is the Y component of FD. And why is that? Because FD is perpendicular to A at a distance, right? And what's a moment? It's a force times a distance. So the Y component of FD times L1, which is the distance that exists between point A and the vertical component of FD, is going to, if I multiply those two together, FD, the Y component, times L1, that's going to cause a moment. It's going to make it want to twist around this way counterclockwise. And that counterclockwise motion is a positive moment. So that's just by convention, and that's something, it doesn't matter if the force is pointing in the positive y direction or the negative y direction or anything like that. It's what direction it makes it turn that determines whether a moment is positive or negative. So a clockwise moment is going to be positive, and that's going to be positive. So this sine of theta times FD times L1 will give me a positive moment about point A. Now we can sum moments too. So let's look at FC here at point C. FC is going to be pulling down, and it has a perpendicular distance between it and point A as well, right? It's also L1. Now you might say, oh, but it's further away. It's L2 away as well. So we need to find like the hypotenuse of L1 and L2. Wrong. No, we don't need to do that. All we care about is how far it is away perpendicularly, right? So if you can imagine even just like tying a rope from FC, or from point C to point D, FC, as long as it's still the same magnitude, doesn't matter how far away it is in the Y direction, it's how far away it is in the X. That's the moment arm that we care about. So FC times L1 is going to be a moment about point A, but it's going to twist it the opposite direction. It's going to go clockwise, right? So it's going to cause a negative moment about point A. And we can add that moment to the moment caused by the Y component of FD, and if the Y component of FD happens to be bigger than than FC, which is all Y component, then we'll have an imbalance there. If they equal each other, then it's zero, right? And so if we look at FB now, if we look at FB, it's a little bit different because the Y component of FB is in line with point A. So Y over H times FB times L2 is going to be, well, sorry, not times L2, but there's no perpendicular distance between the Y component and point A, so it would be times 0. So there is no moment caused by the y component, but the x component of FB does have a perpendicular distance between it and A. So the y component, the part that's going in the x direction, or sorry, the x component that's going in the x direction, x over h times FB times L2 is going to cause a moment about point A, and that's going to be a counterclockwise moment, so it's going to be positive. So you'd have to add all three of those together, like we show here. Sum of the moments about A, so equal all that, and then we do // n, and we get 141.75. Let's plug those numbers in that we've got so far and make sure that we've got those right. So our resultant force that we calculated up here was 103.56. Phi, the angle from the x-axis up to the resultant force, we calculated to be negative 16.8087. And the moment about point A, we calculated the sum of all those moments about point A was 141.75. Let's see if those were correct. Move that guy. All right, so we got those three correct. That's good. So to get the moments about point B, C, and D, you're going to do the same thing that we did over here to get the moment about point A, but you're just going to have to look at it from the perspective of, say, point B. Now, from point B, the force B is not going to cause anything because it's just a force about there. You can see obviously there's no distance. I have to have a force times a distance to have a moment about a certain point. Since there's no distance at all between force B and point B, there can be no moment caused by FB. But a force at A and force at D and force at C all have distances between there. So depending on their orientation, they may or may not cause a moment about point B. I'll leave that to you guys to kind of figure out. Good luck with everything. See you guys.